My name is Lou Ruzzi, PennDOT District Bridge Engineer in the Pittsburgh area, and I'm doing this presentation today with Nikki Bedillion from JMT, who was a designer on this project. I also have Tyson Hicks from Joseph B. Fay, the contractor, and assisting him, Michelle Olszewski, also with Joseph B. Fay. This is going to be a three-part presentation. I'm going to be talking about the bridge selection, the bidding, and the timeline. Nikki will talk about the design issues, and then I will follow up with the construction photos and video. For a couple of years now, our district wanted to do an ABC project with prefab elements and to build it as quickly as possible. The bridge you see there, the 288 L10 bridge, Main Street Bridge in Wampum, Pennsylvania, was a structurally deficient bridge that was in a rural area with a smaller ADT, about 4,600 cars per day. But it did have a challenging detour. And we chose this site because if something did go wrong, it wasn't going to be a major catastrophe to the traveling public. This did have a 22-mile detour on the project. Again, just some pictures of the bridge. It was down to one lane by the time we did the project. Some of the fill had already come out of the side of the arch, and you can see the exposed rebar on the side of the arch there. This one-lane detour actually, or one-lane bridge actually worked to our advantage during construction. I'll talk about that later. We did bid this project A plus B X. We had RULDs in the project of $36,000 per day. We were concerned about how high the RULDs were because this was one of the first time we did a project like this in our district. We were concerned that contractors may not bid it, or maybe the bids would come in too high. As part of that, though, we advertised the project, limiting the maximum number of days to 17, which we thought we could build as part of the pre-construction schedule that we developed, but we wanted a minimum of 9 days that were bid. We did have 6 contractors that bid on the project, and as I said, Joseph B. Fay did win the job, mainly because they bid the job for 9 days. Now, a few days after the project was let, Joseph B. Fay did approach us. They wanted to do a detour with a temporary runaround, and they were asking us to pay for that out of the bonus money, about $324,000 if you counted all the days involved. But we denied that request because we really wanted to see how fast we could do this bridge. Now, if you look at the contract amount, that was $1.685 million, but the bid amount with the A plus BX was a little over $2 million there. See to your right. Talking about the project timeline, we let this project on April 10th of this year. As normally with PennDOT, it's about a 2-month process before the contractor actually gets notice to proceed. Now on this one, what we did was we asked for a letter of intent, which permitted them to start doing their shop drawings around May 27th, and that allowed pre-ordering of the steel, the railings, and the bearings as a result of doing that. You can see by the timeline that we had the precast pieces, the shop drawings were finished and approved by July 2nd. The rolled beam shop drawings were accepted by May 27th. The beams were delivered to New Creek Shop, who was the fabricator that put all of the precast pieces together the week of June 16th. They actually did a dry fit in their plant near the end of July. And the beams had been fabricated at another shop, Shanefelder's, which is about 2 hours away from the New Creek's plant. And now, all right, now I'd like to turn this over to Nikki to talk about some of the project goals and the design issues on this project. Nikki?
Thanks, Lou. When we were first awarded this project, PennDOT's main goal was to replace the existing arch in less than a month. This isn't something that District 11 normally does, so it was new to them and actually new to us. One of their main concerns, Lou mentioned, was that the contractors weren't going to bid on this the structure, because we were actually forcing them to do this in between 9 and 17 days with the disincentive of $36,000 a day. That was pretty high in comparison to the cost of the structure. So that was one of their main concerns during the design process. PennDOT also requested that we did not use any post-tensioning in the superstructure or the substructures. They wanted to use a newer material, ultra-high performance concrete. This material started to be used in the United States early 2000, but it's new to Pennsylvania. And what this material is, FHWA has done a lot of research on it, and it's been shown to be very durable to connect the precast pieces. It has a compressive 28-day strength of approximately 21 KSI. Another requirement PennDOT had was to make it a jointless bridge. So if at all possible, they wanted us to use integral abutments if it didn't affect the structure too much. The design process, PennDOT recently developed standards for ABC for substructures in 2013, but this particular district never had used them up to this point. So what we did a lot of research of other states' details and other successful projects. We read a lot of lessons learned, try to narrow down what we thought would work for this particular project. We researched a lot of FHWA's publications. FHWA has a connection details manual that actually categorizes different connections. The Class 1 category includes connections that have been used multiple times, and Class 3 have only been used once. So because this was new, we focused on just using the connections, the Class 1, because they've already been proven to be useful and successful. After all this research, we presented multiple superstructure and substructure types to the district in a report format. We summarized the different structure types, the cost of the structures, and the length of time to construct the different structures. And then that gave them the opportunity to pick what they wanted to do. They also requested that we worked with the community of Wampum Borough. The Wampum Revitalization Committee recently purchased all of the property around the bridge, which they plan on using for recreational activities. So PennDOT requested that we work with them. We prepared renderings for them. They got to choose the aesthetics of the new bridge, the color of the stain on the aesthetic treatments, and the paint on the steel beams. As I mentioned before, FHWA has a connection details manual. You can see here. Ben Bierman from FHWA requested that if anybody wants this, they can contact him, and he'll send you this manual. Here's the construction schedule that we had to prepare. Because PennDOT was concerned about limiting the contractor and receiving the high bids, they really wanted to make sure that this bridge could be built in the 17 days. So instead of a typical construction schedule of different tasks being done hours and days, they requested that we do it per hour. Our initial schedule showed that the bridge could be built in 17 days based on a 24-hour workday. Here's a picture of the prefabricated structure. PennDOT decided that the most economical structure and the structure with the shortest construction time was a 78-foot rolled steel beam structure on integral abutments. The superstructure consists of 3 two-beam modules. A rule of thumb when designing these prefabricated pieces is to keep the pick weights under 100 kips. So while designing the modules, we had to keep in mind the pick weight. We also had to design for the hydraulic opening. We contacted local steel manufacturers to make sure the sizes of the beams were readily available, and actually our first design included beams that were only rolled every 3 to 6 months. So we decided to use beams that were rolled monthly, so we didn't hold up the contractor in any way. A big factor in the weight of these deck modules was the weight of the barrier. We didn't want to waste time in having the contractor deliver the modules to the site and then having to pour the barriers and wait for them to cure. So we determined that if we used lightweight concrete in the deck and the normal weight concrete in the barriers, that we could get a pick weight of about 118 kips. We had to make sure, we worked with PennDOT to make sure this could be delivered to the site. And by doing this, having the barrier connected directly to the module, we saved an extra pour, which in turn saved time in the field. PennDOT requested a 3D model put directly into the structure plans. The slide that you see here is what we put in there, and that also came along with a very detailed construction sequence, so the contractor could see what our design intention was. Here's a typical section. The beams were rolled, and then they were delivered to the contractor. The contractor placed the deck and the barrier on the beams using conventional methods. They then allowed the concrete to cure prior to delivering the modules to the project site. Because of the 118 kip pick weight, we had to do a thorough constructability analysis. This pick weight needed a 550-ton crane, so our analysis had to include the layout of the modules and the crane due to its size. This crane actually required another crane to assemble it. So we had to make sure that we had enough right-of-way acquired, and there was room to assemble all of this. The substructures consisted of precast pile caps, back walls, cheek walls, and wing walls. Because the abutments were integral, they had to be supported by piles. We had corrugated metal pipes cast directly into the pile caps, so when the pile cap was delivered to the site, it would just fit over the piles. Basically, the corrugated pipes allowed for some tolerance for the contractor when driving the piles. You can see here that the front face of the caps and the wing walls were cast with the architectural surface treatment. Here's a section through the abutment showing the steel H-piles and the corrugated metal pipe in the precast pile cap. Because the piles had to be filled with grout, we decided to weld angles onto the piles so the angles could support the substructure and the superstructure while the grout cured. This way, the contractor didn't have to wait to place the superstructure, and that saved them approximately 8 hours. During construction, the contractor decided to change this sequence, and he actually didn't pour the grout until after the superstructure was placed. All the connections between all the substructure pieces were grouted splice couplers and mechanical splice couplers. The sleeper slabs were placed and grout was placed below them. The approach slabs consisted of 3 pieces. The 2 exterior pieces were cast with the curb attached to it. Leveling bolts and grout ports were cast directly into the pieces. Leveling bolts assisted the contractor in getting the slabs to grade. And then the grout ports allowed for the contractor to pour grout beneath the pieces. Once the approach slabs were placed, the contractor did the closure pour at the integral abutments using Class AAA accelerated concrete. That takes about 24 hours to cure. After the closure pour, the longitudinal joints in the approach slabs and the beam deck modules were filled with the ultra-high performance concrete. And because the contractor decided to heat these joints, the ultra-high performance concrete cured in about 24 hours. Here's a picture of the longitudinal joint detail for the UHPC in between the deck modules and the approach slabs that we used. On the right is a detail I think FHWA is going to make standard. the one that we used hairpins for the reinforcement, but I think FHWA is going to have straight bar studs coming out of the deck modules. We had told you that Newcrete was the manufacturer of all the precast pieces. During the initial shop drawing review, what Newcrete did, they built a 3D model showing all the reinforcement and how all the pieces were going to fit together. And they found some inconsistencies. So designer, owner, and the contractor, we sat down and we worked through all this, made decisions at this meeting, and that did a lot to help the shop drawing review process move along. Another thing, the contractor did a dry fit of the structure. They actually put all the pieces together. I think in the future, this should be made mandatory in the specification. When they did this, they found out that one of the wing walls didn't fit, so it had to be recast. If they would have waited until it was out in the field, it would have been too late. So I think this is definitely a lessons learned for future projects. I'm now going to turn this back over to Lou. He's going to go through the construction.
Thanks, Nick. This is a picture you're seeing at Newcrete's plant. Again, these beams were fabricated at Schoenfelder's plant, which was in Uniontown about 2 hours away, and then shipped to Newcrete's plant where they could place the concrete deck and the barriers on top of the pieces. Overall, this project was done in 7 days. That's 7 days of closure, but as I said to you earlier, we were allowing the contractor to go and work ahead of time prior to closure and do some work. They actually were able to get in there 7 days ahead of time under that single lane closure to do approach slab work. That would be the base, sub-base, the base paving. They were also able to get in there and do 8 of the 12 piles for the pile cap, drainage work, and pipe placement. We also had a time-lapse video camera on the job, which we'll show near the end of the presentation. I got a lot of good pictures there. Starting with day one, again, this was on August 18th at midnight, 12:01 is when the closure started. The demo of the existing arch started right away with excavators and hydraulic hammers. Now, the contractor had 48 hours to demo and clear the debris from the stream, but they were able to do this all in 15 hours. So they were done about 5 p.m. on Monday with the demo. These are pictures showing the excavation for the abutment cap and the piles. Wanted to mention here too, the piles were driven to a 60-foot depth on average, anywhere from 57.5 feet up to 68.4 feet. These are pictures of how close we had to get to the existing arch. You can see how close they had to do that after it was demoed. There was a piece left in place there, and they were able to drive those piles next to the arch. Also, then the photo on the right was the cut piles being cut to the correct elevation for the abutment caps. Moving on to day two. You can see the laborer there, the welder, welding angles on the piles, as Nikki mentioned earlier. It's kind of a tough position to be in if you had to be this guy doing this, but I don't know that we had much choice, because you either have to attach the angles this way or excavate out around it and come in and fill in that area afterwards. So they felt it was quicker to do it this way. Also, then during day two, they had slope protection done in front of the integral abutments. Still on day two, the cranes were being mobbed into place. There was 3 cranes on this job, a 550-ton, 222-ton, and a 100-ton crane. The crane rental wasn't too bad. It was about $5,000 a day, but the mob in and out was $28,000 in and out. Paid that cost twice to get the crane in and out. The 220-ton crane was used to help set up the 550-ton crane, which, by the way, took 9 truckloads of crane to get this crane delivered to the site. The 100-ton crane was used for the approach slab and sleeper slabs, and we'll talk about that later. There may be an opportunity to not use that crane in the future. And again, the 550-ton crane was used for deck modules and the substructure pieces. This is some photos of the prep before the abutment caps were placed. Again, the placement of the angles were done so that we could do the grouting, which while the rest of the bridge was being constructed. Moving on to day 3. We're starting to place the abutment 2 cap using the 550-ton crane. Another picture of the same. This is a picture of the lifting lug used to lift the crane. Now we're placing the back wall on top of the abutment 2. Placement of the cheek wall. You can see where those pieces come together. There was a gap, and we had to go in there and place grout to close up that gap. That gap. We also had a picture of the wing wall going in on the right. These are the form line wing walls. We used a pattern called random cut stone for the form liners, and we used a brown or tannish stain to go over this at the end, which you'll be able to see later. We did do a mock-up ahead of time just to make sure that the stain did turn out the way we wanted to. The deck modules are being placed. They actually did this in 3 hours on day 3. GMT thought this would take 24 hours, and the contractor actually bid 10 hours for this work. But again, it was done in 3 hours, so that was a surprise. Moving on to day 4, there's a picture of the module, elevation views. Super start and starting to look like a bridge here. Everything's starting to come together. This is the sleeper slab subbase being placed and compacted. Actually, placement of the sleeper slabs and approach slabs. So view looking underneath the bridge. Some problems with the approach slab. It took about twice as long as expected. 8 hours on the south approach and 6 hours on the north approach. Part of the problem was when it came from the fabricator, it was supposed to be a 13-inch thick slab, and it was actually 14-inch. So they had to make adjustments in the subbase for that problem. In retrospect, the contractor thought that they could have placed this approach slab using accelerated concrete. We wouldn't have saved time, but it would have saved rental on the 100-ton crane. Now, another suggestion from Ben Bierman, who happened to be at the site for the ultra-high performance concrete, was to use sand instead of stone to help level the approach slab, and that's something we could consider as a lesson learned for some future project. Again, this is the leveling screws is a picture on the left, along with the lifting lug. That was how these screws were used to help level the slabs to the correct elevation. This is the placement of the approach slab on the 2A. We had a 6 mil plastic bond breaker underneath that to be able to have the approach slab slide between that and the sleeper slab. This is a view of the joints, the ultra high performance joints. Note the smooth finish on the picture on the left. This is something that, again, another lesson learned is we would rather have a rough finish on here to help with the bond of the ultra high performance concrete. And one way you can do that is spraying on a product that creates a gel that prevents fines from adhering to the surface. And then at the end you wash it with water once the concrete is cured, and then you have a rough surface. Again, on the photo on the right, you can see the picture of the longitudinal joint. This is a picture of the closure pour being done. This is the piece between the integral abutment and the approach slab using accelerated concrete. Side view the same, closure pour. Another view looking underneath. Now we're starting to get into day 4, basically repeating the process that was on the other end. This is on abutment 2, with the deck and the approach slab being, or the approach slab being placed. This is burning off the lifting floor hook, which, again, as part of that, the epoxy coated got burned off, so the contractor had to go back in and touch the rebar up with epoxy. Moving on to day 5, again, a little bit of the same on the other side, placement of the approach slabs. It's a view looking at the abutment 2, closure pour again on the other end. Moving on to day 6, this was the day the ultra performance. Oh, wait a minute here. We have a lead inspector that showed up on the job. His name Top Cat. This visited the site fairly often, and they actually found a home for him at the end of the job. Starting with the ultra performance joints, this is a view looking into the mixer. The morning, we got there at 6 in the morning on that day, and they had to do a lot of cleanup prior to. I believe it rained the night before. We had to get a lot of the debris off the deck and prep, and I finally started getting around 8 o'clock, I believe they started. This is a picture of the ingredients for the ultra high performance concrete. The picture on the left is the concrete with the aggregate. On the right, you got the picture of the admixtures with the ice. The ingredients themselves are water, a water reducer, a workability retention agent, a concrete accelerator. The fibers themselves, which I'll show you a picture in a minute, they were ½ inch long. They were so fine that they could go through a hypodermic needle. Now, the order the laborer did to mix this was he went with the water, then the cement aggregate that's coming out of the white bag there, then the admixtures, the fibers at the end. Now, by adding in this workability agent, that allowed the contractor to have about 2 hours of workability, which they didn't need all that, but it did allow the mix to come out like a pancake batter, which we'll see in some other photos. This was a very expensive mix. We were at $6,000 per yard on this concrete. Fay also used 2 mixers on the job, which contained about 0.6 yards of concrete each with 2 buggies. They also had to have a 480 kilovolt generator on site to be able to do all this work. There's a picture of the fibers on the right. You can see how fine they are. One problem we've had on this job and another job in our state was this clumping issue. When you do go to put these steel fibers in, sometimes they clump. Now, you don't want to take that then and shove those into your mix. You actually have to remove those and then replace that amount in the mix. So I believe it was about 200 pounds that we actually had to add back into the mix as a result of this clumping issue. That's just a view looking into the mixer. On the right, you can see the ultra-high performance concrete being dispensed from the mixer into the buggies. We had to do a couple checks before we said the mix was okay. One was a temperature check. Typically, the manufacturer, Lafarge, of the ultra-high performance concrete wanted to see temperature between 63 and 69 degrees. On this first mix, ironically, it was 72.6, but Lafarge, who was on site for the job, said that was okay to move forward. Another check we do is a segregation check. You can see the float table there on the left with the mix looks like a pancake. You want to have the diameter of that pancake about 7 to 10 inches. We had an actual average of about 9.4 inches, so that was adequate for this site. Again, a picture on the right, you can see the UHPC coming out. It looks like pancake batter. There's the mixer, or I'm sorry, the buggy on the left. The photo on the right is photo. We're starting to place the ultra performance concrete. You can see the chutes that were used to keep it in the joint, but because of the grade of the bridge, they had to use fiberboard on top of those joints, or else it would have went over the sides and even out of the joint itself at the end of the bridge. You can see the one laborer there trying to corral that UHPC back into the joint. and then the fiberboard was placed over top of the joint on the photo on the left. And again, that was a medium density fiberboard that was used. One problem we started having, though, as soon as we started pouring this, was we started losing this ultra high performance concrete in the joints. And what had happened was there was voids that were at the bottom of the approach slabs, and it was starting to leak out at a pretty good rate. So the contractor had to hurry up and get in there and put some 2A in there and choke it off so that around all the edges of the concrete, so we wouldn't lose any more material. There's a picture of the leak being plugged with the 2A. Now, as you go through this pour, we were constantly checking for voids in the joint. We're sounding it with hammers. And wherever you had those voids, then you had a place that was called a chimney to actually cut into that fiberboard and then place ultra high performance concrete in there and just basically just jam it in there with rebar just to be able to get rid of all those voids. And so it was constantly being checked as we went through the project. The one idea that came up that might be used to be able to find these voids more easily is maybe use plexiglass to be able to actually see where the voids are while this process is going on. This is the joints basically near the end or about the middle of the day on Saturday. These are the UHPC cores. The goal for a lot of these, for these cores, was to be 21,000 PSI in 28 days, 14,000 in 4 days, and 12,000 PSI in 12 hours. We actually had 19, just under 20,000 PSI, 19,889 in 24 hours. So it was definitely reached the strength we needed at the appropriate time. Also, to help increase the cure time, make it quicker, we used blankets, heater blankets over the joints, which got up to, we had the temperature anywhere from 90 to 120 degrees, and that saves 24 hours of cure. Also on the right there, we're starting to put in the 10M barrier, PA 10M barrier that was on the job. Moving on to day 7, more placement of the bridge rail. Guide rail was also placed. We started to do the approach paving on Sunday morning. And this is a picture of the UHPC joint after, a few days after the bridge was opened. And parts of it had to be grinded where we had the chimneys, but other than that, it came out pretty good. They finished all the binder placement, top course asphalt, line painting, and guide rail on Sunday night, and it was opened up at 10:30 at night on Sunday night. This is just a little under 7 days, 6 days, 22 hours. We also placed a epoxy overlay on this bridge, but we couldn't put it on the bridge until the moisture content in the UHPC joints had gone down. They were worried about, the manufacturer of the epoxy was worried that would actually blow off the epoxy if we did it too soon. So we had to wait 28 days for that to cure. And then under traffic, we did the we did the staining under traffic prior to this closure on the 27th and 28th, and then on the 27th and 28th we did the epoxy overlay, which started at 9 p.m. on Friday and was finished by Sunday morning about 8 a.m. Now there's a final picture of the bridge. I've gotten a lot of good comments about it so far. It doesn't even look like an ABC bridge. We're very pleased with how it came out, and you can see the staining and the bridge itself there. I'm going to show you a video right now. It's going to be quick. It's about 2 minutes long. This is where day 1 they're going in. That was the pre-closure work with some of the pile driving done. Now the demo starts at midnight on day 1 of the closure. We had a brief period there where the generator blocked the bridge, blocked the video camera, so we had to get that moved out. We also went on to place the stone along the stream. did a number of different details like grouting the abutment caps, waterproofing, doing some backfill, starting to see the superstructure being placed there. Grouting was going on under the approach slab as all this work was being done. Getting close to the ultra-high performance joints being placed here at some points. Grout was being placed under the approach slabs as all this work was being done. The railing was the joints had been placed by this point. The railing was being placed on the last night. You can see traffic going across already, and then some excavation going on adjacent to the bridge. This was part of a commitment we made to the community for a ramp down to the creek. So overall, in conclusion, we thought we had a very successful project done with less than a 7-day closure. If you add in the bonus that the contractor got, he actually got done in 7 days versus the 9 he bid. He got $72,000. The cost per entire project, if you go based on the bid amount, was $640 per square foot, about $200,000 extra more than a normal job, but well within the $800 per square feet that we see on average in our district. If you just look at the bridge cost itself, it was about $1.3 million. That was about $472 per square foot. Lessons learned, as we talked about earlier, we may want to look at pouring approach slabs. Could have saved on some crane rental, possibly using plexiglass to cover the UHPC joints to see the voids. And again, overall, the community was very happy with the project and commented as such. Now, just final thank yous here. A project like this doesn't happen unless you have cooperation from everybody, and that includes a commitment on part of our PennDOT to want to do this project. And so I'd like to thank Scott Christie, who's Deputy Secretary for Highway Administration. My boss is Dan Cessna, Sherman Sirianni in the district. Tom Macios is our Chief Bridge Engineer. Jim Foringer is in charge of our construction unit. Mike McCart and Dave Raybuck were on site every day. They put in a lot of time out there, especially Dave, with construction. Also like to thank Nikki and her team, JMT, the designer. Thanks to Joseph B. Fay, our contractor, Tyson Hicks, Dennis Watkins, Jackie On, and Michelle Olszewski, and finally the New Crete, the prefabricator, Russell Dixon, the engineering manager. And that concludes our talk for today, and we'd be happy to take any questions at this point.
All right. Thank you, Lou, for such an interesting presentation. At this point, Ben Bierman will moderate the question and answer period. We have lots of questions that came in through the question box, so we'll try to answer as many as possible and finish the webinar no later than 10 minutes after the hour. Ben?
Okay, thanks, Adirad. Lou, Nikki, great job on delivering the presentation. Folks, we received about just under 35 questions prior to the webinar. I grouped them into 5 categories. We have questions that pertain to design, those that pertain to what we'll call planning, construction is the other category. Then we have cost and inspection. And of course, we received a lot of questions during the webinar, and I see them being posted on this chat. We're going to go ahead and tackle the ones in design first. So, Lou, Nikki, just chime in as you see fit, and I'll go off with the first question. Can you list or can you provide any insight on the codes or manuals that were used to design the precast abutments?
Well, overall, we have a PennDOT structure design manual part 4 that's used, kind of the overarching manual that's used on a project, but also Nikki used the ABC toolkit, the PennDOT precast standards. She also talked to Utah and MassDOT on some of their projects to come up with the details. Nikki, do you want to add anything to that, or is that about covered?
That covers that.
Okay. The next design question, and I can chime in on this one. Are there guidelines available for determining the required lamp length at the UHPC joints? Nikki or Lou, can you let me tackle that one?
Sure.
Okay, so you'll see in the presentation that Lou and Nikki provided, was the use of hairpin lap details for this particular bridge project. And that's a good detail. It's what we sort of call our first, what we'll say, first category of ultra-high performance concrete details. And Nikki had mentioned in her discussions that Federal Highway Administration is coming out with further guidance with the detailing of ultra-high performance connections. And she's correct on that. And this new document that we're coming out with will be available in the next couple of weeks as part of that EDC deployment effort that we're doing that Mary Lou mentioned earlier in the news presentations. But to answer the question directly, and again, it's because Pennsylvania is sort of on what we'll call the innovation curve. They're way ahead of it in terms of using ultra-high. But we're seeing detailing that can be simplified. And the use of a non-contact lap joint, straight bars, in lieu of a bent hairpin bar can be used in the same type of detail. The development length that you would see on something like that would be about 8 bar diameters, which is about a third of what you would do in your current design code. And that's because the material, the embedded steel, is embedded in ultra-high performance concrete. So I just want to kind of tackle that one, if you guys don't mind, and we'll move on to the next question.
Ben, just to add to that, we had a hairpin rebar detail that we included in on a job, which I know today Federal Highway doesn't say you have to use, but since this was the first time we used it on a PennDOT job, we wanted to include that hairpin, that overlapping rebar in the joint.
Absolutely, and in fact, when you all came out with this detail, the timing of our information didn't come till afterwards. So what you all did was nothing wrong, absolutely perfectly fine. But moving forward with some of the research that's available, we do have that ability to clean it up. And again, it's just the timing. You guys are ahead of the curve. It's as simple as that. Let's move on to the next question. Let's see here. What was the bridge deck width, and how many girder lines were used for the superstructure?
The out-to-out width
while she's looking that up, we had 3 sets of 2 girders, so it was a total of 6 girders that were used.
Yeah, the out-to-out width was 35 foot 3 inches, 2 11-foot lanes, a 4-foot shoulder, and a 6-foot shoulder.
Okay.
And part of the reason we did that, because we had a sidewalk on there previously, and we wanted to make it a little bit wider without providing the sidewalk.
Okay. And then what about like the overhang? Did that follow your typical AASHTO guidelines, or is there something that's PennDOT specific with the overhang design?
The overhang followed Design Manual Part 4.
Typically what that is about half the beam spacing is what it's limited to, and if you get beyond that, then you have to do a special design, which we did not have to do in this case, right, Nick?
Right.
And the service life of your bridge, is this a 50-year, 75-year? What do you guys kind of...
Well, we're expecting 100 years out of this bridge if we did it right.
Excellent.
Tyson guarantees it.
There was a question that came in during the presentation. Why the use of the epoxy overlay?
Well, there was 2 reasons. One, when you look at the deck with just those joints, it wasn't very pretty, so we wanted to kind of cover up the ultra-high performance joints. In other words, the concrete of the UHPC didn't match the concrete of the modules. And then also, we've been starting to do that on some of our jobs where putting on a epoxy overlay extends the life of the deck. We're hoping that this will prevent us from having to do a deck replacement much more than 50 years. Now, when you do this, you're marrying yourself to the life of the epoxy. Now, we've got varying cases where we've seen it last anywhere from 10 years, 8 to 10 years or so. We've got manufacturers that are telling us it'll last 15 to 20. So we'll have to see. Maybe with this ADT, it'll be more the latter than the former.
Okay. I just thought an important question that came in the question pod. Were the diaphragms between the 2 beams required by design? Now, Nikki, I would like to add to that. I don't know if you want to tackle it or if you would like me to answer that one.
You can answer that, Ben.
Okay. Yeah, I would like to. They are required. Now, what you'll find in design, they're not required for your typical, lifting and placement and stability calculations. Where they are required has to deal with the placement of the ultra-high performance concrete. And now we've seen this in other jobs. It's very important that when you're placing the ultra-high or really any type of ground concrete material with adjacent elements, that you don't get differential movement when the material is being placed into the joint. So that diaphragm, whether you all used it, Nikki, for stability reasons, again, for delivery and placement, or if you had the foresight to see, like, look, we also need this because we're going to have these buggies, coming, bouncing up and down as we place the UHPC, and you need to keep that all in line. It's okay to have the deflection, so as long as all the units are deflecting at the same time. But when you get a differential deflection occurring, you're going to be working that joint opening and closing, and you're not going to be able to get that bond. So, Nikki, I don't know if you wanted to add to that question. It's very important. It's something that we're kind of learning as a lessons learned as we're doing this ultra high, but it applies to any material that you're putting into those joints.
That diaphragm wasn't needed structurally. It was basically just used for the stability of the modules in connecting them. We thought it would be easier for the contractor to include them.
Yep. Okay. There was a question about your epoxy overlay. How long does it take to cure?
That was cured in less than 1 day, right, Tyson?
8 hours.
It was about 8 hours.
Okay. Let's move. I want to jump down to the planning category of questions, and we'll pick up some design ones as we go along. How did the environmental permits influence the accelerated bridge construction design?
Well, as I mentioned earlier, as part of the demo, we had really the only thing was that you had to get the debris out of the creek within 48 hours. So I really can't remember anything else that influenced it other than, no, I really can't say. Nikki, was there anything else besides that?
No, besides the debris in the stream, there was no other issues. I mean, that would have been the same if conventional construction would have been used. So the ABC didn't affect the permit at all.
What about from when we talk about environmental, the NEPA process, the public input? Did you all approach the public or do a public meeting to say, there's a couple ways that we can build this project, conventionally accelerated. If we do accelerated, we have to take access to the site. And if so, did you all get any type of feedback from the public on the approach?
We did explain the project to them. We kind of went into the project figuring we were going to use ABC techniques. It was a small group of people that attended the public officials and public meeting. I believe it was around 20 people that attended, and they really didn't have an issue with the way we were doing the job. Everything was pretty much positive towards it. They were happy they were getting a new bridge, and they certainly weren't complaining. It was going to be done in 17 days at the time. So, especially
with that type of detour you mentioned.
Mm-hmm.
You talked about the A plus B plus X method, and I guess that's, in the incentivizing it. Lou, can you elaborate on what the A component is, the B component, and the X component is?
Well, the A is the bid price, and the B then is the number of days times the RULDs. And so the X is the number of days, the less days you have, in the end, whoever bids the lesser days, then you're going to end up with a lower total bid. And that's how Fay was able to get the job.
Okay, and that's the A plus the B makes that X component, and that's how you all make that decision. So.
Well, we thought it was good to have on this project just just to make sure that the contractors knew we wanted to get it done quickly. Of course, with the RELDs in there, that was another incentive to get it done fast as well. It was a penalty that if it, that they went over, that was the risk that they had. So, and you could tell by when the contractor approaching us about the temporary runaround that they were concerned about it as well. But I have to give them a lot of credit in this case. They didn't argue about it too much, and they buckled up and got the job done quicker than we thought. And I couldn't ask for a better contractor on this job. Everything worked out well.
Okay. I'm going to jump to the construction questions. So was your contractor required to submit a detailed erection drawings and calculations prior to showing up to the site? That would be as part of their shop drawing review process?
Yeah, the erection plans submittals were approved prior to work commencing.
Okay. Let's see here. Can you please describe how the advanced pile driving was completed adjacent to the active traffic?
There was enough right of way on the abutment 2 right side for us to get the drill rig in, and as well as first we had to pre-drill that side, and then we got the pile driving crew in, and we drove. On the left side of the bridge, we actually obtained CSX property, right of entry, in order to do that.
Okay, and there was a couple of questions about your typical work day. Did you all work 24 hours every day? Was it, what was it like from the contractor's perspective in terms of doing the accelerated portion, in terms of stress, labor, and things?
Right, yeah, well, you obviously want to balance out a day and a night shift. And typically, I would say on average, we worked about 20 hours a day on site.
Okay, and was that 7 days, or were you working 4s and 5s?
No, it was 7 days. It was once we started midnight Sunday, we were committed to work straight through until it was done.
Okay, and that was for that 7-day period right there. Did
Correct.
you all? You were going to be at 7 days, or did you think it was going to be 9, or?
Well, that's a good question. There was a couple components of work that was critical in how fast we were going to be done. The pre-drilling and the pile driving was a very important aspect of the job. To get that right so that when the precast abutment came in, the cans that were showed earlier slide over the pile. That had to be right on the money. There was a couple inches of play, but for driving pile 60 feet in the ground, that was critical. So once that happened, then we had in mind that we were going to be able to complete the job before 9 days. But where we got a little bit of confidence going was once the caps were fit well over the pile.
You had an advantage too, where you didn't have to restrike the piles. That saved you a day, right? As well.
Yeah. What happened was we drove some of the pile, like the question was asking. We drove that prior to the 7-day shutdown. They were our test piles. So when we did the dynamic pile tests, it showed we had enough bearing capacity that we didn't need to redrive. So that helped out a lot.
Did you see any sort of, I'm getting questions here about the pre-drilling and why was it used? That's to set your piles, though. I mean,
yeah, the abutment 1, the alignment of the pile was behind the existing structure, but at abutment 2, it was you were going to have to drive through the foundation. So that's why pre-drilling was selected, to drill through the existing.
Now, let me ask you this. If you weren't able to get that early access to do the prowl driving, do you think you still would have been able to do the bridge in that 7-day time frame?
No, because you would have been, I don't think it would have been exactly 2 days, because that was the wait period of the, once you test pile to reach strike. It wouldn't have been 2 more days, but it probably would have been another day.
Okay.
So grand total 10, you mean?
No, of 8 days.
Okay.
Wow. Okay. From the contractor's perspective, with the ultra-high performance concrete, were there any issues placing it?
Well, obviously, it was our first go-round at it, and it is, it is a different material than what we're used to using. But I would say just, making sure that your false work under the joints are watertight. Other than that, you don't finish the product. It's a self-leveling. It really, it wasn't anything. There wasn't anything difficult about it.
Okay. Let me hop on over to the planning group again of questions, the planning group. But these are more specific to your program, Lou. And there's a lot of discussion about your big P3 that's coming up, and you might want to elaborate to folks who aren't in the Pennsylvania area that what this P3 is about. And then there's sort of questions about, well, how does this accelerated bridge construction fit in with your program just in general? So let me start off with this first question, and we'll talk about the P3 too as well. Given your experience with accelerated bridge construction, do you feel it is a good approach for other projects for your state?
Yes, I do. I don't know it's for every single project that's out there. In our district in particular, we got 2 other projects that we're planning, a superstructure replacement, and then we actually got a grant from Federal Highway to do a SPMT move. I know there are other districts that are doing projects like this, one to the south of us and one over near Allentown and over in the east. And so I think it's starting to pick up steam. I think people do want to try it. There is still concern, I'd say, with a lot of designers that, it is new technology, and, they want others to go first and then, see how good it is and then possibly follow from there. As far as the P3 program goes, I believe the number is around 560 bridges that we're trying to do in a 3.5-year period. We're expecting the development team, which consists of designers and contractors and finances people, banks, in some cases, to own and maintain these bridges after they're built for 25 years. And that includes bridge inspections and the maintenance of the bridges. Right now we're currently evaluating proposals from 4 teams. We're going to make our announcement near the end of October, and then the successful team would start somewhere around the beginning of the year with all their designs and construction. Again, then they have 3.5 years to get all their bridges built. How ABC fits into the overall program, I mean, we're kind of dipping our toe in the water on these jobs. I'm personally hopeful we can do more of them. I like the challenge that went along with this job, and we certainly got enough structure deficient bridges. It'd be nice to be able to do some this way. And I think probably expect there's going to be a certain percentage of ABC within the P3 program. I don't know what that exactly is right now, but I know Tom Maciosi in our central office was fielding questions on about 20 different new concepts that would be part of that program.
Okay. With that, we're approaching this 2:10 time frame, so I know there's more questions that are out there, and we'll definitely go ahead and work on getting those answered and getting them posted to the site. With that, I'm going to hand this on over to Adirad to give us a closeout.
All right. Thank you, Ben. Thank you, Lou, and thank you, Nikki, for a very great and very informative webinar. And thanks to everyone who listened to us today. And with that, we will conclude this webinar and hope to have you again on November 10 for our next webinar. Thank you, and have a good day.